Welcome back after the short break, and what we are discussing so far, that the CE amplifier with cell biased arrangement with CE, that bypass capacitor CE in parallel with RE. And what we said is that input to output gain, it is having this expression, and let we rearrange this expression and let us see how it looks like. Maybe it is having some meaningful expression. So, this is denominator part, it is 1 plus G m into R e, and then we do have 1 plus S into R e into C e. And if we further rearrange, what we will be getting, that this factor we can take into the numerator. So, numerator part, it will be G m into R c multiplied by 1 plus S into R e C e divided by. So, this factor, it is getting multiplied here. So, we do have 1 plus S into R e C e plus G m into R e. Now, this is independent of frequency, this is also independent of frequency. We can take together. So, 1 plus G m into R e, we can take them together, and then if you take it as 1 plus G m into R e as a factor. So, what we are getting in the denominator, it will be seeing, but let me write the numerator part, 1 G m into R c multiplied by 1 plus S into R e into C e divided by 1 plus G m into R e. So, we are taking together, and then if we take this factor as out, we do have 1 plus S into R e C e divided by 1 plus G m into R e. So, what we have here, it is one part is this one, which is independent of S, independent of the frequency, and then we do have the other part, it is dependent on frequency. In fact, if you recall that this part, it is same as the previous case when the C e was not there, and due to the C e, then we do have this additional part, and note that it is having a 0 at S is equal to minus 1 by R e and into C e, and also a pole at S is equal to minus 1 plus G m into R e divided by R e into C e. In fact, you may approximate this location of the pole. So, pole location, it can be approximated by considering this part, it is dominating, and R e part, it is getting cancelled, and then you may say that this is G m into R C e. So, what we like to say here, it is this is what we have written, that the expression of the gain, voltage gain, it is not only this part, rather it is having a frequency dependent part. So, since it is having pole 0, I think it is better to go a little deeper into the frequency response of this A naught itself. Now, instead of telling this is A naught, I should say A naught S, which is function of frequency. So, let us try to sketch the Bode plot of this gain. Unlike the previous case, this portion it got changed. So, let me clear and then let me try to plot the gain or magnitude plot of this A naught. So, A naught is having of course, we do have low frequency gain something like this, and which is assuming that this part it is more than 1. So, we can say that it is above 0 dB. So, it is having a gain like this. So, which is coming from this part, and then we do have one 0 here. So, once it is having a 0, then its frequency dependent part it will be changed and it will be linearly increasing. So, the corner frequency here it is 1 by R e into C e, and then once you see the denominator part and at some higher frequency, which is 1 plus G m into R e divided by R e into C e, and that point we do have a pole. And once we have this pole, we can say that the variation of this gain with frequency it got compensated by this pole. So, mathematically we can say that once we have this part dominating over 1 and this part dominating over this 1, then S and this S they are getting cancelled. Then we do have R e and C, this part is also getting cancelled, and then 1 plus G m into R e, that is also getting cancelled with this. So, what we have here it is G m into R c. So, in conclusion what we said is that the gain here it is basically G m into R c, and the gain here it is G m into R c divided by 1 plus G m into R e. And location of this the pole here, which is 1 by I should not say 1, this is rather let me write this is 1 plus G m into R e divided by R e into C e. So, if you see the this expression and this expression, they are differing by this factor 1 plus G m into R e. In fact, if you see, since this is Bode plot and then omega it is in log scale and y axis is also in dB, that means the data got converted into log. So, you can say that the ratio of this and this is consistent with the ratio of the location of the pole and location of the 0. So, at this point we do have a 0 and then we do have a pole. So, anyway, and beyond this point of course, the gain it is continue to be remaining constant. Earlier now if we recall, if it is say fixed bias where the gain it was G m into R c. So, there the gain it was like this, it was continuing like this. So, this is the gain for C e amplifier with fixed bias. And on the other hand, if it is if we have say self bias and if we do have only R e, then the corresponding gain it was continuing like this. So, this is self biased and with R e only. On the other hand, if we have self biased, but then we do have both RE and CE, then in the low frequency before the CE it is really showing its effect. Before this 0 frequency, it was matching with the gain of this self biased circuit with RE, and beyond this point then it is having a changeover starting, and then once it is reaching to this point, then it is catching up with the gain of the fixed bias. So, the self bias circuit with CE, it is having both the behavior. One is for self biased with only RE at low frequency, but then if you consider sufficiently high frequency, then the corresponding gain it is matching with the fixed bias. And of course, this will be appearing in the frequency response, and in addition to, if I consider the coupling capacitor here and then the CL here, of course, their corresponding effect it will be obtained by considering their the high pass behavior coming from C1 and Rin, and then low pass behavior coming from RO and CL. So, if I consider this part, effect of that part, depending on the input resistance of the circuit, which may be R1, R2 coming in parallel, and then rest of the things. So, depending on that, we may be having say a low pass behavior, sorry, high pass behavior, and if we say that this kind of high pass behavior it is coming from C1 and R in of the amplifier, and the corresponding cutoff frequency it is in fact 1 by R in into C1, and on the other hand, if I consider say C2 which is sufficiently high compared to CL, then this RC and the CL it is showing the low pass behavior, and let me consider the low pass behavior, it will be somewhere here. So, it is having low pass behavior, but then its cutoff frequency it is sufficiently high, and the cutoff frequency it is coming from RC and then CL. So, if I combined say this part and then the blue part which is having 3 components, and then we combine this one, what we will be getting here it is the overall frequency response it starts from here, and then it goes with this blue line, since this is 0 dB for the passive circuits, and then it is going here, and then again at high frequency this 1 by RC into this CL. So, this part it is coming there. So, the entire circuit frequency response it is having a behavior like this. So, what are the different poles and zeros are there? This at this point we do have, this is a indication that it is having a pole at high frequency, and then also it is having a pole at this frequency. Then we do have a 0 at this frequency. Then we do have a pole here at this frequency coming from C1 and Rin, and also it is starting from a slope of 20 dB per decade. So, that means it is having a 0 at 0 frequency. So, it is having 1 0 at 0 frequency, we do have another 0 here, and then the 3 poles. So, that is how the frequency response of this entire C amplifier with RE and C looks like. In fact, I was having different slide to explain, but we already have discussed this part. Again, just to summarize here, the frequency response of this entire circuit, it is having a pole here coming from C1 and R in, and then it is having 0 here, which is coming from R e and C e, and so this is 1 by C1 and R in, and then we do have frequency here, which is 1 by, I should not say 1 by 1 plus G m into R e divided by R e C e, and then we do have high frequency pole, which is coming from 1 by R c and C l. So, that is the frequency response of the C e amplifier. Now, one additional information I like to say here, while say this part, it is indicating that it is location of this pole, it is depending on one R c time constant. Likewise, this 0, it is another, it is coming from another time R c time constant, and so is for the high frequency pole. Whereas, for this case I do have different kinds of expression, but it is having a meaning in case if you approximate that the numerator part, it is practically G m into R e. So, this expression of this cutoff frequency, it becomes G m divided by C e. So, what does it mean is that whenever the C e it is looking into this node, the effective resistance it is seeing here, it is not only this R e and then R pi, but most important thing is that we do have one active device here. So, if you are applying a voltage here, that voltage it is directly appearing as V b e or V e b, and that is making a huge current flow because of this G m. So, the net resistance seen by this C e, it is, I should say that R e in parallel with whatever the R pi we do have, in case if I consider this is connected to ground, and then in parallel with 1 by G m. So, this is getting dominated by 1 by G m. So, the corresponding R c time constant is basically this resistance and then C e. So, as a result, whatever the corresponding pole we are seeing, it is 1 by G m into this C e. So, this time constant, and that gives us G m divided by C e. So, this C e in combination with the equivalent impedance coming from this active device, which is 1 by G m, it is giving us the corresponding corner frequency. Now, in case if depending on the value of this, of course, C 1 and R in, it is possible that this corner frequency it may exceed this corner frequency, but most of the time what we do, we take the value of this C e sufficiently high, so that this corner frequency it is not exceeding this one. That is because you may remember that our main purpose is to get an amplifier having a good gain. So, this is our main frequency band, and if we are having higher band, it is better most of the time. And so, if one of them it is exceeding the other one, whichever is lying on the right side, that defines the lower cutoff frequency. In this case, the lower cutoff frequency it is defined by this, but in case if we take a value of C 1 very small, and in case if it is crossing this point, and then this may be defining the corner frequency. So, typically we try to see that value of this CE, it will be taken sufficiently large. So, that in optimum case we may say that these two corner frequencies they are coinciding. So, depending on in case if it is exceeding this point, of course, it will be having the behavior of the frequency response, it will be slightly different, but nevertheless I should say that I do have to define the lower cutoff frequency. I do have two candidates, one is GM divided by CE, another one is 1 by R1 R in and C1, and whichever is higher I should say that is the lower cutoff frequency. So, what we are saying is that let me write in terms of omega. Omega lower cutoff frequency, if I say omega L. So, that is equals to max of these two candidates. One is GM divided by CE, the other one it is 1 by C1 R in. So, whichever is higher, that defines the lower cutoff frequency. Of course, we can convert this into hertz. So, this is 2 pi f L. On the other hand, the upper cutoff frequency, there is no ambiguity. So, 2 pi f u, which is omega u. So, that is coming from 1 by R o, which is R c, and then C L. I think that completes the analysis part of the CE amplifier and then common source amplifier frequency response. Let us see some of the numerical examples. So, here we do have this common source amplifier, CS amplifier, and this part this part we already have done, namely if the device parameter k multiplied by W by L, it is given to us, then threshold voltage is given to us, supply voltage it is if it is given to us, and then bias elements are given to us. From that, what we have obtained is that we obtained the DC operating point and then small signal parameter, namely GM and R naught in case lambda is given. But anyway, here lambda is not given. So, at least small signal parameter wise it was GM, and from that GM we obtained this voltage gain AV, which is GM into RD, and then input resistance we obtain here it is primarily R1 parallel R2, and then output resistance we obtain same as this RD. So, this part we have done before. Now, today in addition to that, in case if we have these two capacitors value and also the CL is given to us. So, this is C1, this is C2, and then we can find what will be the corresponding R in, and then we can find what will be the cutoff frequency, lower cutoff frequency. So, in this case what will be the lower cutoff frequency? Omega L equals to 1 by C1 into R1 parallel R2. So, whatever the value it is we are getting, we can calculate ourselves, and likewise since C2 is much higher than CL. So, we can say that this series connection CL it is connected here. So, the series connection of CL and C2 it is giving us the load capacitance, which is load cap is equal to C2 multiplied by CL divided by C2 plus CL. Now, you see this value here, it is the C2, it is 10 power minus 4, and then CL, it is 100 picofarad, 10 power minus 12 divided by 10 power minus 4 plus 10 power minus 12. So, this is what we said, that the denominator part, it is dominated by this. So, we can easily write that this is 10 power minus 12, right. And so, the upper cutoff frequency omega u, it is equal to 1 by the CL and this R d, and R d it is given to us, this is 3 k, 3 into 10 to the power 3, and then CL, it is 10 to the power minus 12, no sorry, we do have 100 pico, 10 to the power 10, sorry, 10 to the power 10. Anyway, so this is becoming 10 to the power 7 divided by 3, or we can say that 10 divided by 3 mega radian per second. Okay. And we can convert this in terms of the in terms of hertz, and what we will be getting is that if u, it will be in the order of few hundreds of kilohertz, right. So, that is 10 divided by 3 into 2 pi. So, roughly it may be 400 something kilohertz. Okay. Whenever we are talking about CL, it may be coming from maybe next stage, or maybe from measuring probe capacitance or instrument. Typically, in hardware lab, we have seen that the CL, it is in this order, somewhere 30 to 100 picofarad. So, that with that CL and this practical value of this R d, you may get this upper cutoff frequencies like this. Lower one, what we have, it is R 1 and R 2 if they are in parallel. So, that is how much? This is R in equals to 3 into 9 divided by 12. So, that is 9 divided by 4, right. So, this is 1 by C 1, it is again 10 to the power minus 4, and then R in, it is 9 by 4 k, 10 to the power 3, right. And so, that gives us how much? This is yeah, no, this is what we said, is it 10 microfarad, sorry, this will be 10 to the power minus 5, earlier we have written minus 4, anyway it is still, this approximation is valid. So, we do have yeah, so this is 400 divided by 9 radian per second, and so this is how much? Around whatever 40 maybe 40 less than 45. So, maybe 43 radian per second and divided by 2 pi. So, if I divide by 2 pi roughly 6. So, that is becoming around 7 hertz. So, that gives you some idea that what may be a typical value of the lower and upper cutoff frequency of this common source amplifier. So, likewise you can consider say CE amplifier also. So, again for this circuit we have done the mid frequency range analysis, namely by considering supply voltage and then RB, we obtain the base current, and then from the beta we obtain the collector current. It was you may recall that it was 2 milliampere current, or you can calculate here IB equals to 20 microampere, and from that we obtain GM. It was IC divided by VT. So, that was 1 by 13 ampere per volt, and so from that we obtain the gain, which is GM into RC, and RC it is 3.3 K. So, we got something around 240 gain. Now, similar to the previous example, here we do have this additional information. So, C1 and C2, it is given to us as say 10 microfarad, and we do have the CL here, which is a 100 picofarad, and then input resistance of this circuit, it is RB in parallel with whatever you say R pi, and R pi. So, I should say R in equals to all practical purposes it is R pi, which is beta divided by GM. So, that is 1.3 kilo ohm, and then the lower cutoff frequency, it is omega L equals to 1 by C1 R in. So, that is 1 divided by 10 power minus 5 into 1.3 into 10 power 3. So, that gives us 100 divided by 1.3 radian per second. So, roughly you can say that this is how much, around 70, in the range of 70, around 70 to 80 radian per second, and if you convert into hertz, then it will be in the order of maybe around 12 hertz, right. And on the other hand, the upper cutoff frequency, it is omega u equals to 1 by R c into the CL. CL it is dominating with respect to C2. So, this is equal to R c, we do have 3.3. So, CL it is 10 power minus 10 farad multiplied by 3.3 K 10 power 3. So, that is equal to 10 power 7 divided by 3.3. So, that is becoming how much? This is around 3 roughly 3 mega radian per second, and in hertz that is in the order of 500 kilohertz. So, that is what the typical lower and upper cutoff frequency. So, in case if you are doing lab experiment with whatever the components it is given to us, then you will be getting the lower and upper cutoff frequency of this circuit. So, likewise, if you consider the C amplifier having RE and C, and if we have the similar kind of value of this R or rather R1 R2, it is given such that the current here it is similar, namely 2 milliampere of IC, and then here we do have the C1 and C2 similar to the previous case, 10 microfarad, and CL also it is given to us, it is a 100 picofarad, and depending on the value of this R in, of course, we will be getting the input resistance, and of course, as I said that for the lower cutoff frequency omega L, we do have two candidates to define the lower cutoff frequency. One is 1 by C1 and R in, and the other one it is GM divided by CE. Now, if you see that previous case, if we consider that R in equals to R pi, okay. So, of course, there will be a doubt that why we consider R pi, but for the time being let you consider if it is in this R in is equal to R pi, and there we have seen that the lower cutoff frequency it was coming from this part, it was around 770 radian per second, around this value. Now, let us calculate numerical value of this GM divided by CE part. GM it is for IC equals to 2 milliampere, this is 1 by 1.3 ampere per volt, and CE it is given here. So, the GM divided by CE, so that is it is becoming 1 by 13 into CE, it is 100 microfarad. So, that is 10 power minus 4, and this is becoming how much? This is rather 10 power 4 divided by 13. So, what we can see here it is this is definitely higher than 1 by C1 into R in, and so as a result in this case practically then this becomes 10 power 4 divided by 13, and its value it will be somewhere in the close to 1 K, maybe around 800 radian per second. And in case this is the situation, then actually we should have considered this R in equals to R1 parallel R2 in parallel with R pi plus R e into 1 plus beta. And since this part it is higher than this one, so then R in it is approximately equal to R1 parallel R2. And if you see this R1 parallel R2, earlier we have discussed its value, it was no, we have not discussed. So, we have to consider these two in parallel, and since we do have 3.3 K here and 9.9 K. So, what we will be getting here, it is 9.9 K multiplied by 3.3 K divided by 12.2. So, if I cancel this part, it will be 4. So, in fact, this is becoming 9.9 divided by 4, 9.9 divided by 4 K. So, if I consider even say 9.9 divided by 4 K and C 1 it is say 10 microfarad, then also this G m divided by C E, it is becoming dominant. But of course, in case if you are picking say this value, this C 1 it is say maybe 1 microfarad, then of course, the candidate to define the lower cutoff frequency, it will be the first one. Okay. So, most of the time what you do that this value of this capacitor, it is almost 10 to maybe a few 10 times higher than this one, or rather sometimes it may be even 100 times higher than this one, C 1. On the other hand, C 2 normally we take same as this C 1. Now, this numerical examples, as I said, that indirectly it is giving you some idea that what may be the typical value of this C 1 and C 2 to get the whatever we have discussed, that lower cutoff frequency and upper cutoff frequency, right. And upper cutoff frequency, of course, again it is coming from this R C and C L, and R C it was in the similar value, or at least its order of magnitude, it is similar to the previous example. So, the upper cutoff frequency again it will be in the order of around few hundreds of kilohertz. So, that gives you some idea that what may be the practical value of those lower and upper cutoff frequency you can get, or the frequency response you do get. Yeah. So, what we have covered today, let me summarize that today and previous day. So, the first part, this part we already have discussed before, and today we have covered this part, the frequency response of the CE amplifier having fixed bias. And when we say fixed bias, it may be only with RE or RE in parallel with CE. And then we have discussed about numerical examples for common source amplifier, common emitter amplifier with two types, one is fixed bias, another is the cell biased. Sorry, this is cell bias. Today we have discussed the cell bias part, not the fixed bias. This is the typo. Yeah, so we have covered the numerical examples for common source, common emitter, with and without CE and RE, and then that gives us indirectly some design guidelines. So, later on if we find some time, probably we may revisit to this design guidelines, but for the time being at least we got some idea that what may be the value of this C 1, C 2 and C E to get meaningful upper and lower cutoff frequency. So, that the mid frequency range it will be sufficiently wide, and as we said that this is in the order of say or roughly 50 kilohertz, and this is in the range of maybe tens of hertz. So, that gives us one amplifier which is definitely suitable for audio kind of application. I think that is all we do have. Thank you for listening.